Hello everyone, myself Anil Sharma from Impulse Technology. In this video, I will demonstrate you how to make first solar cell modeling and simulation using SETFOS software from scratch. Let's get started. Now I would like to start the SETFOS 5.2 version. So I click on SETFOS 5.2 and click Run as an administrator to provide a background permissions. Now it is loading the examples and material database and will check the license. Now on the top of the screen, new features window has been opened. You can click next to check the next features that is updated in the current version, and whatever new updates, new features comes, that will show on the top of the screen. So I can check next updated feature by clicking on next button. Now I can close this window to check the main screen. For help purpose, we have a tutorial and manual. You can click on help, and manual and tutorial will be available in PDF formats. I would like to start from scratch. So I will click on file option and click on new projects by clicking on this new button. Now default there are 3 layers has been added: surrounding, unnamed and substrate. So this tutorial, first of all I will perform the optical solar cell calculations. Now to perform the optical solar cell, I have to enable the absorption module. So I will enable this absorption by clicking on this sun button. Now solar cell is surrounded by air. Therefore I will rename the top and bottom layer, and I can define the name of my top layer, that is called air top, and on the bottom side I can define air bottom. And 2 layers should not have same name. Identical layer name should not be allowed. Now I will click on unnamed layer and I will add multiple layers in between the air top and bottom layers. For that I will click on this add button to click add layers. Suppose I want to add 4 more layers. So I have to add 4 more layers apart from one unnamed layer. Now I will rename the first unnamed layer, that I will change it and make it as a glass, where the thickness of this glass layer is not important because it will treat as an incoherent and transparent. Then the cell comprises of ITO. So I can define the ITO next layer name, and I can change the thickness 125 nanometer. You can take the units as per your needs: nanometer, micrometer, millimeter and wavelength dependent. 4 options are given to you in all the options by clicking on this drop down icon. Now I will click on unnamed 3 layer and change its name. I will define the name of this next layer, that is called P dot, and define its thickness, that is called, suppose I can take 50 nanometer. Next layer I can change it. I can define P3HT PCBM. That is my next material. I can take suppose 100 nanometer thickness, that is already defined. And finally I can define my background bottom aluminum material. Here I can take this same thickness. Now I have defined the name of my all layer with their thicknesses. Now I have to set the refractive index of my each layer. So I just click on this ITO first, and ITO refractive index is not constant. So I just click on this refractive index tab it is not constant value, it is dependent on wavelengths. So I will click on choose the file option from this drop down. Click on import button to import the refractive index from our library. Library is available inside the C drive, program files, Fluxim, SETFOS and MAT, that is stand for material. In this directory you can find the material database. You can scroll right to check all material property that already exist, optical and other semiconducting complete database that you can visualize on the screen. Sequentially all materials are there. Since I have to choose ITU refractive index, so I will select this itu.nk and click on open it. Now it is loaded. It is showing the preview of real and imaginary part with respect to wavelengths. Similarly, I will click on p dot layer and then click on this refractive index tab and click on this file options and click on import button. Here I can choose my p dot nk refractive index. Just scroll this and reach up to P letter. Now here all combinations of P dot refractive index I have found it. Whatever you want to use accordingly, you can select it and click on open button. It is now loaded. Similarly, I can click on P3HT PCBM and click on file options, click on import option. I can reach to P3HT PCBM.nk file and select open. Similarly, I will click on aluminum, click on this constant and select the file, click on import and select aluminum.nk and click on open it. Now all material refractive index has been defined. Additionally, set the refractive index of glass. So I can click on glass layer and refractive index of glass is not wavelength dependent. It is a constant value which is 1.5. So I can define here n equal to 1.5 and set the refractive index of air layer from the top and bottom, that is equal to 1.0 or simply 1 we can define, and similarly for bottom layer I can define 1.0. Top and bottom layer in solar cell calculation must be transparent and coherent. And also the convention for the direction of light in coupling in SETFOS, the light is always arriving from top. In case of this current structure, the incoming direction is from the glass, from this glass to the active layer. This also the reference direction for the calculation of the reflectance and transmittance of the thin film structures. Now I will set this glass layer as an incoherent. I will click on this general button and set as an incoherent by activating this checkbox. If any layer thickness larger than 500 nanometer you define, then the number of calculations points should be reduced to not more than 100 points by checking this element box and entering 100 value. If this step is omitted, the kernel might be blocked, since per default SETFOS calculation profile with discretizations of each nanometer. A layer of 1 millimeter required at least 1 million calculation for each wavelength. So be careful with thick substrate and reduce the number of elements if high precision is not strictly needed. So I can define here the element equal to 100. and I can change the thickness of my this glass substrate. Now the simulation is set up and can be run by pressing this run button. Before that, I can define name of my project. Solar underscore cell. This is my name of project that I have defined here. Now I can click on run button. Now the program has started the calculations. Now calculation has finished. Among the various results, you will, for example, find the graph of layer absorptance, where you can clearly see that in the spectral region between 375 nanometer to 650 nanometer, the P3HT PCBM is highly absorbing, which is showing with this color regions. So different colors are showing different layer absorptance properties. Now based on this example, I will vary the thickness of active layer P3HT PCBM and see what is impact on the maximum generated short circuit current and apparent color of the cell. So I will click on this general and click on sweep mode by enabling the sweep setting. Now define the thickness of P3HT PCBM layer as a sweep parameter. So I click on it and select the P3HT PCBM layer with the thickness as a parameter, and the starting value that I want to define, that is 10 nanometer, and the stopping value that I can define, that is 200 nanometer. The step size of thickness that I can mention, suppose 10, so that after every 10 steps it can run the calculations. Now I click on this cursor so that status will become OK on the bottom side, and the unit nanometer is also specified already. You can choose according to the thickness of your active layer. Now I will press this run button to start the simulations. Now I will click on photocurrent. The short circuit current as a function of P3HT PCBM thickness, that is called this pink graph. I can hide other graph, that glass graph that is called red one on the bottom side. I can hide this one, and this blue one is also on the bottom, zero line, that is I can also hide, and this green one is called for P.ISC, short circuit current, and this aluminum is in the below sides, and this is P3HT PCBM pink color photocurrent with respect to thickness. Now I will run my first electronic solar cell simulations. So in this section you will learn to fully simulate the optical and electrical behavior of bulk heterojunctions organic solar cell. From this optical simulation of solar cells. Now to couple the optical absorption module of this device, I want to enable the dipole diffusion module. So I just click on this battery sign to enable the dipole diffusion equations. Now this dipole diffusion setting will be enabled once you click on this battery. Now we set the P3ST PCBM as a semiconducting layer and import the electrical material parameter file from the database. So I click on this P3ST PCBM. You can click somewhere else first. Then click on P3ST PCBM to find this general option. Now I will set it as a semiconducting type. P3ST PCBM as an active layer as a semiconducting. By activating this checkbox, this tab will be enabled. Here I can click on import button. And I can find the P3ST PCBM electrical material file. This is all EM file dot extension electrical material. And I can select that and click on open. Multiple combination of P3ST PCBM are given with TREVs, with SRH, with the small recombinations, and click on open it. By default, all the layer materials parameter will be added in the user interface for this P3HT PCBM layer. Right side you can find the layer structure tab and the energy levels. I want to hide this. Click on this one to hide it. In following, the electrode with their corresponding work function need to be defined. The top electrode is called P dot. So I will select it as a P dot. I will click on this general button and select as an electrode. And I can define the work function that I can change from 4.5 to 4.8. And similarly, aluminum that I can set as a bottom electrode, and I can click on this general button and click on electrode. And ohmic type it is already selected. There are two type of option is there in top and bottom electrode, ohmic and thermic. Here I can set the work function value here. So we can adjust as per the needs. Now to calculate the current voltage curve, I will go to the drift diffusion settings and select the steady states mode from all four options. So steady states can be performed transients, AC impedance analysis, and IMPS intensity modulated photocurrent and photovoltage spectroscopy. So I select this steady states in this drift diffusion tab. Now when the absorption module and drift diffusion module both are active, the optical and electrical simulation are automatically coupled and charge or exciton generation is given by the optical absorption profile and the generation efficiency of charge or excitons. To activate the optical generation of charge carrier in the P3ST PCBM layer, set the optical generation efficiency to a value of 0 to 1 in a semiconducting tab. This column. Now finally I will sweep setting to be updated. I will click on the sweep setting. Now this time I want to sweep the voltage instead of thickness. So I click on this electrical and select the voltage. Now I want to set the starting value of voltage, that is minus 1.0, and stepping value that I can mention here 1.0. And I can define the step size 0.1. The unit of voltage need to be defined by selecting the voltage Now I will click on start button to run the simulations. Now I will click on this current and you can check it. This is current versus voltage graph, where mean current, anode current, cathode current and recombination. 4 graph will be displayed. 2 of them are overlapping to each other with different color schemes. So this is all about how to make first solar cell in this SETFOS. Similarly, other power conversion efficiency, power density, band diagrams with the bearing of changing the voltage from negative 0.1 value to positive 1.0 value, how the band gap will be changing. Similarly, electrical field on different voltage rising, multiple graphs are there. Recombinations in the form of multiple curve or single curve can also be visualized, or you can play this button to see the curve on different voltage biasing. In the form of curve or in the form of checkboard, you can also visualize it. Similarly, absorptance or particular layer specific absorptance can be plotted. If you would like to more information, kindly contact to Impulse Technology. Thank you for watching this video.